Welcome to our journey into the world of software testing to improve the Cognitive-Affective Map tools. Together we will unlock the secrets to craft flawless applications. Cognitive-Affective Maps (CAMs) are a qualitative and quantitative research tool which were made popular by the philosopher Paul Saggart and act as a specific form of mind maps. CAMs consist of concepts linked by connections which are freely drawn by a participant. Thereby concepts indicate an emotional positive evaluation in green, a negative in red, ambivalent in purple, or a neutral emotional evaluation regarding these drawn concepts. And these concepts are connected by connections varying in strength, and dashed lines representing inhibitory and solid lines supportive relationships. To collect and analyze these data, we have developed three tools. To collect data, we have developed Cognitive-Affective Map Extended Logic, which is an open source software to draw CAMs, and it aims to offer people an easy and intuitive interface on which they could draw their own mind maps within online studies. There's a participant view and a researcher view to set up studies, and it's possible to change multiple parameters of the CAML software to adapt such CAM studies. Another tool aims to analyze the resulting data, which is called CAM-App. Here we're using multiple modules to summarize the resulting CAM data semi-automatically, for example using large language models. And those summarized data can subsequently be analyzed. For example, the CAMs could be aggregated or over 30 network indicators could be computed. Finally, there's a web page to set up and configure CAM studies without the need of coding. Now our central goal is to debug these three developed tools. Thereby, software debugging is the process of identifying, analyzing, and removing errors, bugs, or abnormalities in computer software. It involves the use of specialized tools, techniques, and strategies to ensure that the software performs as intended and meets its design specifications. After these tools have been improved and bug fixed, we will deploy them to a university cluster. This process is of most importance because already around 20 researchers currently using these tools. Imagine you are a valiant knight combating bugs and glitches to protect the integrity of software, and your central task is to notice weird and unexpected behavior of our developed CAM tools and know how to document such behavior, and at best you should be able to reproduce it. I want to encourage you to try and provoke unintended ways of using these tools, like entering things that are clearly not supposed to be there. Before explaining your central tasks, I would like to explain you some technical fundamentals of browsers. Understanding the fundamentals of browsers, including HTML, CSS, and JavaScript, is crucial for software testing. This knowledge allows you as testers to effectively analyze web applications, identify potential issues in the user interface, and understand how changes in the code affect functionality and user experience. Finally, it even enables the creation of more accurate automated test scripts and helps in debugging issues in ensuring the delivery of high-quality, robust web applications to improve our CAM tools. What are the building blocks of web pages? To briefly summarize them, we have HTML, which is used to create the basic structure of web pages, allowing browsers to display content. We have CSS, which is applied to HTML to style and lay out web pages, enhancing the visual appeal. JavaScript brings web pages to life by adding functionality and interactivity. Together, these technologies allow developers to build complex, interactive, and visually appealing websites and applications. While HTML lays the foundation, CSS enhances aesthetics, and JavaScript introduces interactivity, showing the synergy between structure, presentation, and behavior in web development. An HTML document is like a family tree with different members, each playing their own role. Here, document type HTML. This is like telling everyone we are going to speak in HTML language. It's not really part of the family, but it sets the stage. HTML. This is the grandparent of all other elements. It wraps around everything else in the document. The next head. This section is like the brain. It contains information about the document, but not the content people see directly. In the case, it holds a title tag. And the title tag is simply naming the document. Here the document is called first HTML. And finally, body. This is where the document's visible content lives, kind of like the body that does all the action. Here it says, I'm your first HTML file. Each member is nested inside the other, creating a clear hierarchy or family structure. If we would now compile the shown HTML code and add a footer, which represents content at the bottom of a page, we will get the following result. Now to CSS. CSS, as explained, the cascading style sheets is applied to HTML to style and layout web pages. The style argument makes the background of the footer section red. So the bye-bye message will appear with a red backdrop, making it stand out. By defining here style background color red. Now, JavaScript brings web pages to life by adding functionality and interactivity. This code here waits for someone to click on the footer section of a web page. When someone clicks the footer, a small pop-up message appears that says, you clicked on the footer. It's like setting up a fun surprise for anyone who decides to click on that the bottom part of a web page. In the world of web pages, event listeners, like the previous one, are like little spies you place on different parts of a page, like bottom images or the footer, to watch for specific actions by visitors. These actions are called events. Events can be many things. Someone is clicking, for example, a mouse button, pressing a key on the keyboard, moving the mouse over an element, or even loading the page itself. When an event listener detects a specific event, it triggers a response you have set up, like displaying a message. Basically, combining multiple event listeners enabled us to create the Cognitive-Affective Map extended logic tool to collect data. If you want now to look under the hood of your browser, you can open the so-called console, which I will show you on the next slide. If you, for example, want to try around with the example.org webpage, you just can click on it. Now we have opened the example domain. For Firefox now I would click on the right bottom of my mouse, and here in German it's called Untersuchen, or I think it's called Inspect Element in English. I simply click here, and now the console of the browsers opens. Here I can search through the web pages, identifying different HTML elements, or I go directly to the HTML code. And what you see here, what I previously explained to you, this HTML code is structured like a tree, like a hierarchy. And here we could go, for example, to a specific element, like the example domain, and we rewrite it, like say, hello, folks. And now we have changed the web page. We also could change the style of the element, for example, making the element even wider. And that would be changing the CSS of this web page. Sadly, it's not so easy to change a web page permanently. If I'm now refreshing the web page, we have the same web page again. What you also could do next, we have here our console, and now that's where you could enter, for example, JavaScript code, and we could identify any error messages which could pop up. And I could, for example, write here a command like console log, hello world. That would be now printed to my console. I could use also the alert command, and now I get a pop-up which tells me hello world. And that's where you can, for example, change the interactivity of a web page. All shown examples of HTML, CSS, and JavaScript you can find on GitHub, and you can test for yourself if you want. If you would like to learn the basics of web development yourself, here are some links that I used to teach myself these skills. Extremely helpful are YouTube channels from professional web developers. Now you could ask yourself, why at all is this important for my personal life to understand how web pages work? For example, if you're looking for a flight or you are buying products in an online warehouse, you're normally confronted with dynamic web pages. And importantly, for example, price discrimination occurs when a business or seller sets varying prices for the same product or service tailored to different customer groups. For example, flights are sometimes more expensive if you book them using an Apple product, because it could be assumed that people who are using an Apple product have more money. Another important area are individualized product recommendations, which make up a large part of Amazon's profits. Such price changes or different product recommendations are only possible on dynamic web pages, which is basically driven by JavaScript frameworks and other programming languages which are used in the background of a web page. Now I want to give you an overview over software testing, whereby I focus on the following two books: the Handbook of Software Engineering and Software Engineering at Google, and multiple articles which I will reference on the single slides. In order to continuously improve the developed CAM tools and keep them bug-free, we are confronted with software engineering, which is a systematic approach to develop and maintain software. You could imagine that software engineering is like overseeing the entire process of creating a building, from planning to construction to maintenance, making sure everything runs smoothly and meets needs. Programming, on the other hand, is like the actual construction phase, where the focus is on putting bricks together according to the plan. So while programming is about writing and testing code, software engineering covers the big picture, including managing the project and making sure the software keeps working well after it is built. There are central models describing the process of software development. The rational unified process is a detailed and structured approach for software development, which emphasizes iterative development focusing on meeting requirements and building around a core architecture. At the beginning, during the inception phase, the main objectives are to align stakeholder expectations with the project goals and secure the necessary funding. In the elaboration phase, the team details out the system requirements and validates the system architecture to ensure it can support these requirements. The construction phase is where the actual development takes place, aiming to bring the system to a point where it can be deployed. This phase concentrates on finalizing requirements, designing, coding, and testing the software according to these requirements. Lastly, the transition phase is about getting the system ready for real-world use. It involves rigorous testing by system tester and feature user, making necessary adjustments and preparing end users, support teams, and operations staff through training. With the develop chem tools, we now want to go one step back to the construction phase to improve these tools one step further. You also could focus on the spiral model. The spiral model is like going around in circles which each turn you add more details and part to the project, the software, making it more complete while making sure the risk or chances of something going wrong get smaller. Risks are conditions or potential events that might prevent a project from achieving its objectives. Their severity can vary from minor to catastrophic, and their probability of happening can range from highly likely to nearly impossible. It includes important checkpoints to make sure that everyone involved agrees on what the project should look like and how to make it work well for everyone. Such a process model answers two main questions. What should be done next? How long should it continue? Your central task now is to identify existing risks in the developed tools, more precisely, possible bugs. This leads now to our central task, testing these developed tools. But first, what are bugs? In the context of software testing, a bug refers to an error, flaw, or fault in a software program that causes it to produce an incorrect or unexpected result or to behave in unintended ways. Anything deviating from what is required or expected from a software is a bug. The severity of a bug ranges the seriousness of the issue regarding from a blocker, meaning the application cannot be used anymore, to trivial. For example, indicating a minor visual flaw or spelling error. Now, the maintenance of software is a continuous task. For example, how browsers compile HTML could and will change in the future. Or there are updates of JavaScript libraries which are included in our developed tools. It is estimated that more than 70% of software products' total life cycle expenses are dedicated to maintenance, which includes updating existing code, fixing bugs, and making improvements to the software. As an example, you could have a look in the documentation of the different releases of the online study tool Lab.js. Now, what are key characteristics of bug reports? How would you now report a bug you have found in the develop chem tools? For example, you would send the developer team a description of the observed behavior where you precisely describe what have happened and how this deviates from the expected behavior. Ideally, you should also specify the specific steps to reproduce the error to make it easier for the web developer to resolve the error. But now you don't need to remember such key characteristics of bug reports because I created an online bug report template which you can fill out when testing the individual tools. To set up these templates, I included these key characteristics and oriented myself to Bugzilla, which is an online bug tracking tool developed by the Mozilla Foundation, which has developed, for example, the Firefox browser. Now, what are the exact steps to report bugs? First, I would like you to download the detailed explanation how to test these 3 different tools from my GitHub page. Then, to set up your testing environment, I would like you to use the private mode, the private browsing mode of your browsers, so that your testing is not affected, for example, by your browsing history. And then in the next step, you open the respective software, the data collection tool, the data analysis tool, or the web page, and start testing, whereby links to the respective software is provided here in this link, in the first step. Now finally you report bugs or possible improvements in my bug reporting template. I would like to show you a bug I'm already aware of and show you how I discovered this bug, how I can reproduce it, and how I would fill out the bug report. Okay, first I click here and I'm opening the links to the testing materials for the different tools we have developed. Now I want to report a bug for the data collection tool, Camel. I'm just clicking here to open the PDF. I could also download this PDF here. And for every tool, I'm providing you links to the respective software. And for the data collection tool, we have here different possibilities. We can use the default configuration of the software, but we could also use so-called minimal or maximal setting where we have less or more features. And you can inform yourself possible features or possible settings which are possible in the data collection software. If you now want to explore different bugs, I highly recommend to read also the second bullet point, where I make some recommendations how you can test the respective developed tool. Here I just want to use the default setting of the Camel software. I'm just clicking here to open the Cognitive-Affective Map extended logic software. Now I'm drawing 2 concepts. For example, I'm saying it's sunny. Sun is shining, that's super positive. But the sad thing is I'm now start to sweat more. And that's bad. And that would be we would need to have here, for example, an arrow indicated the direction. Because only the sun can lead to more sweat, but sweat is, when we are sweating, we are not influencing the sun. But now the awkward behavior is of the data collection software, if I'm moving these concepts too close to one another, the arrow is flipping, as you can see here. And I also could try out this bug if it may be depending on the area of the drawing interface. But we see the same behavior, for example, here in the left corner. Now, at the next step, we would like to report this bug. Then we open the link to the bug report template. We're saying, okay, I want to report a bug. It's not a spelling error, therefore we would use a Google Docs document. And here I want to report a bug for the data collection tool, Camel. And that is concerning the element, the connections between the concepts. And what's also important for software testing that I know which browser you have used, because browsers are compiling HTML differently, and sometimes we have only issues in specific browsers. And here that's totally correct. I'm using the operating system Windows 10 and the Firefox browser, and that's the current version of my Firefox browser. So that's right. And I'm lazy. I haven't tested the bug on other browsers, which would be super nice if you could reproduce, for example, different bugs in different browsers. Now the important part. I should now describe what happens, including any steps I took before I saw the problem. And here I just copy-paste some text I prepared. If connected concepts are too close to one another, the arrowhead is flipping. This seems to be the case for the whole drawing window of Camel. We have tested it. And it seems not related to the concept type, like if we have a positive or negative concepts. The next now is telling me, okay, screenshots are super helpful for a web developer. Now we could also make a screenshot. And here, for example, in Windows, you could use the snipping tool. I make a screenshot of my bug. Okay, I need to move them close to one another. Now we're seeing the bug again. Now I'm doing the screenshot. I'm saving this picture, my first bug discovered. And now I want to upload this picture. That's my first bug discovered. Okay, here we confirm we have uploaded the right picture. That's nice. Now what we have missed, what we also could do, is there any error message in the console of the browser? And that's why JavaScript is so important. Therefore, here we could open also the console. Then we could try to reproduce this behavior once again. And the text message is totally right. We have added in your concept, in your connector. But now if I start moving it and the arrowhead is flipping, you don't see any error message here. The error message would be highlighted in red. So, okay, we don't have any additional error code to provide our web developer. Now we maybe can check it once again. Okay, we have filled out everything we need. We just click on send. Maybe you have a nice feedback or any additional comment you could provide here. Else you just would click on end study. And now you're redirected to our main page and you have reported your first bug. That's great. It could be the case maybe that this was a bit too fast for you. And the main task, what I want you to do is so-called exploratory testing. Yeah, that's not an online course, it's just a video. So if you want to see the video how a guy is testing the Burger King website because a Whopper was not delivered to his home, you can check out this video, how you would do it to maybe come into the right mindset to be a great software tester. And that's all I really appreciate, and I would like to thank you for any recommendation, any bug reporting in the future of our developed CAM tools. Thanks.